Okay, for this problem, we're told that a table exerts the four forces shown on the floor, and we want to reduce the force system to a force couple system over here at point O, and then show that R is perpendicular to MO. And then I'm going to answer another question that is typical of a problem like this, and while it doesn't ask it explicitly, it'll be useful. All right, so let's begin by just finding the force. So R is the sum of the forces. And this one, we have a minus 200, minus 160, minus 160, and minus 80, all in the K, so that R is equal to a minus 600 K newtons. So there is our resultant. And then as far as the moment is concerned, the moment around O, and we can do this by thinking about the moments around the x-axis and then the moments around the y-axis. All of the forces are parallel to the z-axis, so we don't have to worry about any moment around a z-axis. So let's take the x-axis first. And the 160 Newton force and the 80 Newton force that are actually on the x-axis will intersect the x-axis, so they won't have any contribution. However, the 200 Newton force and the 160 Newton force will both produce moments around the x-axis. It should be relatively apparent that they're going to produce a moment that is in the negative x direction by the right-hand rule. So we're going to have a minus, and I'll put this in brackets, 200 times a moment arm of 0.6 meters here, and then plus 160 times the same moment arm of 0.6 meters. And that is in the I direction. And then for the y-axis moments, we will have no contribution from the 200 Newton and 160 Newton forces. They're both applied on the axis. They'll have an intersection here and here. However, the 160 Newton and 80 Newton that are applied at this far edge of the table will produce a moment around the y-axis. And it should be fairly easy to see that they will produce a moment by the right-hand rule that is in the positive y direction. And so this will be a plus. We have 160 times the distance of 0.9, and then the 80 also times the distance of 0.9, and that is j. And if you do the math here, the moment around O equals, we get a minus 216 in the I, and it happens to be the case that we get a 216 in the J, and the units would be Newton meters. So there's our couple. All right, for this last question, it says show that R is perpendicular to MO, and that's easy enough. We could just do a dot product. So R dotted with MO is equal to a minus 600 in the K dot with minus 216I plus 216J. And remember, the way a dot product works, you would multiply similar components. And if we think about this first term here, the R, that's actually 0I plus 0J minus 600K. So the I and the J and J would dot. Or you could think about this final moment term as having plus 0K in it. So either way, this would be 0. So R would be perpendicular to MO. All right, let's make a sketch real quick of what this would look like, and then I'll show you how to do one other thing with it. So let's grab our force arrow here, and we can make a sketch of the resultant. So the resultant is straight down in the negative K. So here is R. And then we have a moment that's in the negative I direction. So that would be this direction. And then a moment that's in the positive J direction. That's this way. And let me give a double-headed arrow here for these. I always like to do that for a moment. And so this would be a rotation in the negative X, and then this would be a rotation in the positive Y. So you could think about this as MOX, and this would be MOY, and then this, of course, would be r. Okay, so at this point, let me move that label. At this point, we could think about maybe simplifying it further. And what we want to think about doing is maybe moving this r resultant somewhere out in the xy plane so that it would produce the same moment of MOX and MOY. So let me just kind of sketch it out here, and then we can locate that. So I'll just draw some lines that would go to each of the axes. This is some y coordinate, and then this is some x coordinate. And if we think about a position vector that would locate this from point O, we could call this vector r. And then remember, this is our resultant. And it would have to be the case that r crossed with the resultant was equal to MO. So this would be some x in the I plus some y in the j crossed with r, which is a minus 600 in the k, is equal to the moment around O, which was minus 216i plus 216j. Okay, so I crossed into k is a negative j, so we have a minus 600 times x and a minus j. And then j crossed into k is a positive I, so this is a minus 600y in the I, and that's equal to a minus 216 in the I plus 216 in the j. And what we can do is set the I components equal to one another and the j components equal to one another. So if we think about the I direction, we have a minus 600y equals a minus 216. And in the j direction, we have a positive 600x is equal to a positive 216. And if you do the math on either of these, it's clear we're going to get the same value, but x would be equal to y, which would be equal to 0.36 meters. Now, they didn't ask us for that, but it would be the case that these four loads could be replaced by this single resultant R that is a minus 600k newtons, and it is positioned out here at 0.36 meters in both the x direction and the y direction. And that would be it. The other process that a person could use here is just say, well, how far away in the y direction here do I have to move the resultant so that it produces this moment around the x-axis? And so you could say r times y equals MOX, and you can tell by inspection that you would have to move the force in the positive y direction to produce the moment around the x-axis that's in the negative. So you could work with magnitude. 600 times y is equal to 216, and you would find the same answer, y is 0.36 meters. Just kind of a different way of doing it. I actually prefer the vector approach for students, because if you understand a little bit about how vectors operate, it makes the problem very tractable, and it makes it a little bit more resilient to mistakes. There's not many mistakes that can happen when you're just following vector operations. So I think it makes it easier, less error prone. All right, so that's this problem.